it's time to learn how to evaluate the performance. So you just saw that when the code, you saw that FAR, so what are all these things on which we judge the performance of a biometric system. So before we begin, let me I will give you my favorite example here that how biometric can bring a societal change. Here you can see that it's a picture. Hey, so can you recognize her? Afghan girl, right? So she is so basically she is the girl. Her picture was taken by this photographer when she was 12 years old. Camp in Pakistan. Then what happened? 1984, and then he again took a picture in 2002 after 18 years of camp, and it was clear that she is the same girl, Sharbat Gul. So this is the picture which they printed it on their cover page, and the same photographer said like the picture of the same person was claimed, but how can he identify? Yes, this is a same girl. So here the biometric played the role, and this Afghan girl was actually identified by her iris pattern. You can see that the iris pattern here is and the iris pattern here with the picture taken in 2002. And what happened here with the iris code, the distance, the matching distance is Hamming distance, right? So that I will tell you. Right? So when the Hamming distance is calculated between the patterns, then in the left eye it is found 24, and in the right eye it is found 0.31. And these odds are being calculated that like if this is a small distance, the odd is there 10 to the power into 1 that the two pictures are from the different person. Similarly, for the right eye, the odd in 6 million to 1, the two belongs to different person. So it is widely accepted that yes, she is the same girl, and the National Geographic magazine, they acknowledge it, they print it, and what is done? So you say that okay, we have got okay, this is the same girl. Then what has happened? But then a lot of the funds have been created so that these girls their education may be paid off, their medical care may be taken. So this example, let us the talk of the today. This slide is just for the sake of completion of this, because now we are very much aware how a biometric system works. So this is a basic biometric authentication. As we said that features, templates, we are already talking about it since yesterday. The only difference between traditional system and deep learning system, how the features are being extracted. So I have uploaded two animations in your folder. So one I showed you. Please look, just run each and every tab on it, and you will get a lot of idea. So in the machine learning systems, like how the different modality, the features are being extracted, how the matching is done, similar to the deep learning, I was showing you the demonstration, but not many things are there. I showed you, you can have a look over there, and then you can again come back to us. So any difficulty, anywhere you want a clarification. So now, so we know how the authentication is done. Now the question comes that why we are going for evaluation? Why the system evaluation is required? Because what is happening here, there are two impacts. So one is the security impact, another is the usability. Now, when we talk about security, this thing, so we want pure false accept, right? So we don't want anyone, any intruder to join the system, to be given the access. But what are the, because what is happening, these are the repercussions of it. That's why we don't want, right? But at the same time, if we go for high, let us say false reject rate, then what is happening? Because we want, what will happen? The user will get frustrated. User will not be satisfied. So what happens here? Because if there is high false reject rate, then system is rejected, productivity is low. So what is there? We need to somehow take care of both the aspects. We want security, and but not at the cost of user satisfaction. We want user to be satisfied. So what is the decision we have to take? What is the optimal balance for your application which you are working? So evaluation actually provides the data to make this decision. What should be, like we are talking about threshold, right? Matching. So what should be our threshold? So that is on your application based on your data, you can take the decision. So what is to be compared here? All of us know Now, you can see here, so when we talk about samples, they are just raw captured. If you talk about images, just raw images or voice recording. And so, when we are going for digital systems or DL-based systems, basically at the end of the day, we got the template, right? So, what is a template? Whether we are using digital system or the deep learning system, so those features are extracted and in the collection of those, because a template is an amalgam of the features extracted from my, let us say, I'm providing multiple copies of providing my biometric multiple times. So it is just template is all features are extracted and the template is collection of the features, or you can say the learning system, collection of the learned embedding. Now this template is there and we need to. So now what is the for the matcher? The matcher will take two samples here. One is the stored template and another is the template given generated at the runtime, real time, and then it will generate either similarity score or dissimilarity score, what you are comfortable with. So in the verification system, we are going to use this score so that we can determine that whether two biometric samples are from the same person or from the other. So now when we talk about features, right? So what are the features? So what are the features over there? So there are, like, if you go for machine learning, deep learning, so first of all, very basic features, right? So geometric features we started with. So we say that, okay, what is the distance between the eye, nose to chin distance, jawline shape, forehead height, all these simple, right? So if you look at the demo, in which so many features are simple features, machine learning based demo, so many features are given over there. Then we move this one step further. Now we come to this texture-based features. So local binary pattern, for a long time, these features have actually ruled the pattern recognition applications. So local binary patterns, then histogram of oriented gradients, which is shift, surf, all these. Then these features are found to be robust to aging also. But now the third approach, where the state of the art is for deep learning embeddings. So here we are having CNN model, and in the previous lecture you are getting this these words being used. So these are the famous models for the face. So face that are we are using the different loss functions you are talking about, and then you are going to extract these vectors. So maybe anything between 512 to 048. This is, let us say, size of the vector embedding, which is just changed in the previous class, right? Just change the length of the features. So here, when we move towards accuracy, just saw that 99.2% somehow you received. So it is quite good. It was not possible earlier with the machine learning based system, and with the based embeddings, we are able to handle the issues which I highlighted there in the face recognition. So now, variation. So what are the feature representation formats? Some examples are here. If you talk about iris, right, then we are having these binary templates, right? So a template is just these many bits, right? So you can decide what is the how many bits are there. So like if you just saw the example of that search algorithm I took, that iris pattern is being extracted, you can see that one such vector, one such 0, 1 vector is there from both the eyes, and then it is the distances. So then we have vector representation, which is we talked multiple times minutiae. So you just saw that on the fingerprint, some points were being highlighted. So how we are going to store those points, those fingerprint minutiae, by the position, right? This is their position, and then this angle and type. So basically, remember I showed you the pictures. There you have these different types, right? Bifurcation is there, or ending is there, and these are the location. And so with some reference line, this is the image. So later on, when you are talking about at the time of matching the BB, you can shift it and see that how many minutiae are going to be matched. Because if you are moving your finger, maybe the same minutiae point is highlighted, but then the angle is going to get oriented, and then see that how many pieces are matching. This is for then we are going for deep learning embedding. So it is just a vector, right? So you can see a vector of numbers. So here you can see that, and it may be of any dimension over there. So vector of values that is going to represent the relevant feature. So when you are going for a machine learning based approach, then in the fingerprint you are going to extract these minutiae points, right? So let us say you got, for example, 200 minutiae points, right? So, but when you are going for deep learning, then not these minutiae points, but you will learn those features just like where they are identified from the picture, right? So you will just learn a vector like this, not the minutiae points. Several other features are there in the value. And then yesterday we were talking about privacy preserving biometric and syllable biometric. So there you are having the biometric templates encrypted. And what is the point is there? You are not required to decrypt it for the matching. So as I told you in the cancelable schemes which we have developed, the matching is performed in the transform domain. So you are not supposed to extract the original biometric from the transform biometric and then do the matching. So the matching, when you are transforming your templates, the matching will be performed in the transform. So these are just some sample of the, so that you may understand what do we mean by feature space. Now, so as I told you, templates are usually vectors. So here you can see that this is your first vector A, vector B. You can imagine that this is your store template, this is your template which you are giving in the real time. Or now, when these two images are basically, when we are creating it, so we are getting these two vectors. You can just imagine these are the vectors A and B, and these are my descriptor. So this is my descriptor A, descriptor B, and these are your features, right, which we just showed you. So now what we need to do is that we need to calculate similarity between A and B. Right? So let us say, and similarity is considered, basically it is negatively correlated with the distance. So if the distance is more, similarity is less, right? Distance is less, similarity is more. So here you can see that these are okay. So this is just as I told you, if your feature vector is n-dimensional vector. So every data is just one point in that n-dimensional space. For example, when we are saying talking about 3D space, right? The 3D space, one point is there, so it is having x value, y value, and z. Now just imagine your vector of size 3. So we are having n-dimensional space, and this image or this person is just one point that n-dimensional space. Now you can take a very simple example. Let us say not because it is difficult like 512 dimensional space and all. Just okay, let us decide we are making our some feature for ourselves. Okay, let us say we decided our height, for example. So our height, let us say our weight, just a dummy example, height, weight, eye color, and then what else? What can we take? Let us say your skin color, let us say your hair color. Right? So there are 5 dimensions. Now what is happening? Every one of us will be having one value for each of these 5 attributes. It means that every one of us can be represented as one point in the 5-dimensional feature space. Right? So similarly here, 512 dimensional feature space. So every person, like every like is in fingerprint or face, whatever, that will be a point in that dimensional space. And then we can see, okay, who two are close. So in that n dimension, like you know that simple thing, 2 points, how they are calculating distance between them. Similarly, we can calculate distance between 2 points in the n dimensional space. Here you can see that this is just this example. So descriptor 1, descriptor 2, descriptor 3, descriptor n. So this is your first descriptor, this is your second, this is your third. Now we can calculate the distance between. So you can calculate the distance between A and B, AB distance between B and C, and now you can say that the distance between AB is greater than the distance BC, and so the reverse in the similarity, right? So the similarity between B and C is more as compared to A. So if I ask you who two are similar, so B and C are similar, right? So B is not that similar to A. So that is what our task is there. What we do is that we do we normalize this distance. So everything is equal to 1. We can say that similarity is the 1 minus distance. So this is the concept. Right, sir? Now, how to calculate distance? Euclidean distance is the simplest thing. We all know about it. So just to see that in 2 points P and Q, in the two dimensional, this is how we calculate Euclidean distance. Just expand it for n dimension. Nothing. So we can. I will show you in minutes how. So just similarly go on adding it, right? So x1 minus x2, y1 minus y2, z1 minus z2, a1 minus a2, b1 minus b2, whatever dimensions are there, and just take square, add it, and take the square, right? We get the UT. Now here I am using the word DT. Now there are so many distance functions because we are already not much research is done in the machine. So they are having n number of distance functions. Distance function is not a metric, right? When we will call that a distance function is a metric, let's find these properties. Now when we say that, so well defined and finite for all A and B, right? Every 2 points, like you can calculate the distance. And what is this? So we say that if the distance, if you are considering same point, right? So distance is 0, but distance between 2 points that is greater than equal to 0. And then here, whether you are moving from A to B or B to A, right? Whether you are calculating distance from A to B or B to A, it should be same. And finally, there should be triangular inequality. So Pythagoras theorem, I hope you all are remembering, right? So sum of two distances, right? That is greater than equal to the third distance, right? So the distance between three points, right? So if distance function is following these properties, we call it distance metric. Now there are so many distance functions are available for comparison. So here you can see that first of all, distance or it is called Manhattan distance. What is this distance? Simply take the difference between the two. So what is happening here? So what is AI? AI, so that is now I n dimensional. So first dimension, second dimension, third dimension, like that. So just take the difference between the corresponding pairs and add it up, right? So that is how you L1 distance, and this for outliers are important. And for histograms are very, like who have done the processing, histograms are very important features, and they are very simple, and they serve good for many applications over there. Histogram are nothing but we just get the probability of the intensity value. So just draw, because let us say our image can have any value, our pixel can have any value from 0 to, let us say, 255, right? Now, how many pixels are there having value 0, right? How many pixels are there having intensity value 1? We can plot it. Now, this number is going to change if my image size is going to be changed. So what we do is that we just divide it by the total number of pixels in the image, we get the probability, right? So let my picture is n cross n picture. So what is the probability of pixels having intensity value 0? What is the probability of pixels having intensity value 1? If we plot it there, that is what we call it. The simplest feature which we followed in the beginning. Then we have this L2 distance or Euclidean distance. You can see here, just take the difference between the corresponding here, square it, add it, and then take the square. And now this node distance here, just take the maximum of it. The corresponding, so A1 and B1. A1 and B1, which one is greater? Take that. A2 and B2, which one is greater? Now you can understand here it will take time, and here it is much simple. You can see that when we need to do the matching in a hardware constraint system where response time want calculation time, see that it's 5 times faster its calculation is as compared to Euclidean distance. Then we have this chi-square distance. Here you are going to measure like how one distribution, right? What is unlikely that the one distribution from the population represented by us, because that is how these two are different. That is what you are going to get. So all these are very basic one and very famous. Then we are having vector cosine similarity. Yesterday also we talked about. Now you know that the two vectors are there, right? So what is the, I can say, like when you say the two vectors same, they are in their dot product is, so they are in the same direction, right? we say that here you are saying this cos theta, that is the angle. So, and this, like, you are taking this, you are looking how much they are aligned. So, if they are aligned there, okay, similar, they are different, like, simply take sine distance. So, this gives you direction based, right? Because if the direction is same, see it is. Then we have Hammond distance. We just use in case of iris. So, case of iris, used to show iris is say binary difference, right? So, in case of binary what Hammond distance, so we simply count the differing bits, right? So, where there is a 0 and 1, so on the same position I, if it is in one template it is 0, in another template it is 1, we are counting. That's so. These are all, and there are so many others, but these are the very common ones. Now, what are the quality issues in the template matching? See, first of all, we need to take care of class positions, different. Then there might be very small interclass differences. So, like the things, like what happens? For us, it has become difficult. So, like I have a cousin who are twins, so after quite some time, we are able to recognize them. But there are fine differences. But the one who is for the first time, they very difficult. There are fine differences. So we need to take care of those fine differences also, so that we can identify these tools. After that, so noisy or distorted noise, like poor quality. So it is difficult to find out the effect. Yeah. And then that example is for non-uniform lighting. After that, non-universality is there. So you see that missing these lines over there, and then hidden features. Finally, like the issue is how to take care of attacks, because it is not like attacks are happening after this AI has come. Attacks were there earlier also. Now they are, I mean, it's, much in the discussion, and so we'll take up this tomorrow. So now, so the question comes that how we are going to evaluate that. How can we measure the performance of the biometric system? So now we know that when we are going to calculate the distance between the store template and the runtime template, we will get a matching score. But when we are going to do the performance analysis, then we need to analyze behavior of the system, sorry, for different thresholds, right? So how do we fix a threshold? Because based on the threshold only we are determining similarity or non-similarity. Now the question comes that how are we going to decide this? And for that, we need to look at the performance of the system at different thresholds, and we need to decide, okay, for my application, this threshold is the best, right? This is giving the best results for mine. Now remember, I will just show you that a number of biometric error types are there. So error types or error percentage, and remember that the true values when we talk about various rates, that can be I mean, that cannot be completely obtained, right? Or established. But we can actually, we are going to obtain the statistical estimates of the error. How we are going to fix up the threshold, that is based on the probability of the match score. So based on that, we are deciding our. So you can see the estimates of the on the test database. We'll see what is the probability. So when we go for errors, there are two kinds of errors. Basically, there are two hypotheses, right? One is we say that null hypothesis, when we go two samples match, and alternate hypothesis when we say that two samples do not. Right? And remember that these definitions depend upon the application, whether you are going for positive application or for negative. So if you go for negative, the meaning will be reduced, right? So now various terms are being used, and as I tell you, because what happens, your matching engine, that matching engine is deciding whether null hypothesis is true or alternate hypothesis is true, right? And then, so based on this decision, there are actually two types of errors a matcher can make. what are these errors? So let us say, first of all, I will take the scenario of the verification. Later on, we will go for authentication, right? So you understand, verification means one-to-one match. Authentication, that is verification. So first of all, we are talking about verification case. So we are dealing with the, we are saying, okay, when I'm saying I'm Preeti, so that is a one-to-one match. So these are your error, false match, call it type 1 error, or false non-match error, and correct match and correct non-match, right? So here you can see what do we mean by a type 1 error, or say false match, or sometimes we call it false accept. So FMR, false match rate, or false accepted FAR, I mean, they are being used, so don't get confused with it. So we need to decide the false match happening. You can understand like this. There is a match, but that match is a false. Means my system is saying that it is a match, means these two templates are from the same user, but in reality they are from the different. So there is a match, but the match is a false. And with this frequency, this is happening, that is called false match rate or false accept. So if you remember, Dr. Kiran has showed you a graph, right? So the rate, right? FMR and FNMR. These are. Now, false non-match or type 2 error. Here we say that non-match, right? So my system is saying that it is a non-match, but actually it is a match because that is a false. Here you can see that the system is deciding that the two biometrics are not from the same identity while they are from the same identity. And so this is false non-match, and again with the frequency this is happening for your test data. That is how you are going to get false FNMR or FR, right? False reject. Because what is happening? Your system is saying non-match, right? But it is a match. So you are rejecting actually a genuine user, right? A genuine user is being denied. Then we also have two correct decisions, correct match and correct non. So correct match, or you can say genuine match. Here, the how correctly the biometric samples are matching, that is what is. Similarly, how genuine is your non-match, genuine reject. So correctly identifying that the two biometrics are not matching, so the rejection is due. Now, how the question comes, how we are going to compare the systems. First we need to compare the systems. We need to tell something about the performance, and so what is happening? We are going to the simple count of errors. Okay, I'm running it 100 for 100 users, and this is my count. Right. Next time I'm running it for 200 users, this is my count. That is not going to solve. Right? So what is happening here? We will discuss what we are going to do is that. So what is we need to find out false accept rate or false reject. Now when we say that false accept rate, it is basically the rate, or say the percentage of resolution when an imposter is allowed access, right? False accept. Imposter is allowed access. So here you can see that if your false accept rate is just 0.1%, right? Say it's very small, right? And let us say, what does it mean? It means that out of 1,000 imposters, one will be getting access, right? So, so what we say that? So what does it mean? Basically, we say that the probability of the unauthorized person being identified as an authorized one, that is. Similarly, now we have false reject rate. So here the genuine user is being denied. So again, if I'm saying that my FRR is just 0.05%, right? So what does it mean? One out of 2,000 authorized person. Just imagine a airport. So many people are there, and you are in a hurry, there's a flight, and you are stop. Right? So one out of 2,000 in this case, which is very small, but on a large scale system, it is going to fail. So now what are the operations? Remember, we are talking about it, but let us finalize it. Say that, so there, when the matching was coming one, this example, the code which Dr. Raja was showing you, when it comes one, when the same template was, same copy was there, right? You're not saying it is template of the same person. When the two copy, the one is copied, and then you are calculating the distance, right? So, but what is the observation there? If the templates are from the same user, the matching score will be high. Similarly, if the two templates are from a different user, the matching score should be low. Okay. So what we can say, the match score is usually high for matching, match score is usually low for not. Right? So with this note, we have to move forward. Now our question comes that when now our system is ready for work, right? Users are being enrolled in the database, and now my task is to find out whether my system is identifying those users or not. Right? So the question, and not only identify those enrolled users correctly, those who are not enrolled, it should reject. Now what happened here comes this, as I told you, this is the probability density function of the match and non-match. Here you can see that this is the probabilities are plotted. So these are the scores. This curve you are getting for imposters, right? So these are the distances for the imposters, right? And this curve is for genuine users, right? Now the thing is that, and then what is happening? You need to choose a threshold. So what is happening? You have chosen a threshold. So when you have chosen a threshold, then what is happening that because the two curves are overlapped. If these two curves would have been like this, our task would have been very simple. Just choose this threshold and everything is set for us, right? But unfortunately, and let me tell you, these two curves will never get separated, right? They will always be overlapped. So when you are having these overlapped distribution, this is the imposter distribution, this is a genuine distribution, and then you are choosing a threshold. So what happens? These genuine users are coming below threshold. It means that these many genuine users will be denied access, right? And this part of imposter is there are some imposter who have somehow managed to get the score more than threshold. So if they are managed to get the score more than threshold, obviously they will be assigned, right? So here you can see that these imposters, blue color, they are falsely accepted by the system. They are not the genuine user, but system has accepted because they are crossing this threshold. Right? So here you can see that. Now let us say I'm changing my threshold. Okay, I said okay, now I don't want anyone to be there. So I want to make it more secure. So what is happening? Earlier, these many imposters were getting access. Now only these are getting access. Security has increased. But what happened? Earlier, only these genuine users were denied. Now, these many genuine users are going to. So finally, if you are going to move it, this threshold on the right hand side, what is happening? Security is increasing. But what is happening? Genuine users are being denied. Now, if you are moving this threshold on the left hand side, what is happening? Users are happy, but security is being. Now you can see if you want that these genuine users should be given access, and you are choosing threshold like this, now you can see a huge portion of the imposters are being allowed. So that is the problem. So choosing a threshold for a biometric system. So here there are so many hiccups. So first of all, you want a good features, because if the good features are not there, obviously nothing is going to matter. So first of all, you need to see about features, then you work on the distance functions, and then finally it comes on the threshold value. How should you choose the threshold? So that, and that is why we always talking about, and we are saying that it depends upon your application, your requirement. If it's simple class attendance system, no point in choosing, because if I'm taking a class and 50% of the students are standing in attendance, they need percentage. It's very important, right? For them, for their point of view. So things will not go right. So here, this is the, so you can see again the same picture. So here there is a match, here there is a not. So remember, so if you're, I think this I have already explained that, okay, if imposter is somehow generating high similarity score, then the subject will be allowed access. Similarly, here you can see that a genuine user, he is causing a low matching, so he will be rejected, right? So if when this will happen, if the features, if your not features are not accurately extracted, this thing is going to happen frequently, right? Because the original user, their templates are not. So now here you can see that, as I told you, that for biometric application, these scores, right, these score distribution are always going to overlap. Right? You will never get a perfect situation that they are not. So it is not possible for us to select a threshold where false match rate as well as false non-match rate both will be zero. Right? It is not possible. So, and also one more thing is that they are inversely related, right? Because if you are increasing or decreasing the threshold, one value decreases, then other value increases. That is what I showed you. You're moving it right hand side or left hand side. So one parameter you are working upon, the other is going to change. So now, so how we work upon this and we decide the what should be our threshold and what is the best optimal matcher for me, that we express it by using ROC curve, receiver operating characteristic curve. Now here you can see that. So okay, so there is another example. I think I have already covered. Let us say there is a smart card and so fingerprint system. 3% is too much now. 3% FRR, right? And you are using it, let us say, at some facility that people are requesting access per hour. And one day means 16 hours. So you can see that these many people are going to fail. Similarly, if you are going to say that with the same data, okay, 2,000 people are there and 16 hours a day, but here, let us say 80% are genuine and 20% are imposter. Out of those 20%, what is happening? These 192, they are going to be falsely accepted. Right? So just understand the concept. And now, how we are going to estimate our error? Because nobody will tell us, okay, choose this threshold here and this is going to work. Basically, we will run it with our data. How those distribution curves have come. To know those distribution curves, we need to run our patcher with some data. So we are estimating errors actually with the help of the data. So T has to be selected for, threshold has to be selected for optimal fashion. It means that our biometric patcher needs a tuning over there. Right? So we need to tune it so that we are going to, and whenever we get acceptable rates, right, whichever rate you are agreeing with your application, you are going to, and what is the threshold at that point, you need to settle with that threshold, that is your option. Right? So here, now also, here, given this score density, what is happening, we need to compute the probability of your false match and false non-match, and so that we can generate the similarity or dissimilarity estimates. And for this, we need all sort of population. It is not like you have enrolled 100 people and you are checking for those 100 people only. I mean, some outside, like some other people, right? So some imposters are to be there, and only the. So because we are, so as a standard practice, what is happening? A biometric system is trained for all, right? Not only for the same population, but the population which is not actually belong to, not actually stored. Right? So and so remember that all error trade-off studies, they actually, that's some average type of, not very deep, like somebody has decided, okay, I am going to hack it, right? But otherwise, in general sense, some population is there which you are using to test, right, as an input. That is what we do. So remember, because we are going for database, I will quickly cover it. So you need to have, because you are learning threshold from your data and you are executing your system, right? Imagine that you are choosing the threshold. So remember that your data should be a good mix. If you are taking data of one type only, already, obviously system is not going to tune for all situations. So you are in the data which you are using, that there should be population diversity, like good adequate male female ratio, then it's variation, right? Some people are with glasses, some are not with glasses, some weird, some are not, like that, right? Different sensors, different angles images. So you need to, your database should contain all sort of variety of images so that you are using your system. State. Okay. still you need choose all sort of things, right? I told you so many variations over all these. Now, so we got the error rates, right? So what is happening? We are going to create these plots of error rate for different thresholds, right? And that plot is called receiver operating characteristic curve. So here you can see that we are going to take x-axis, y-axis, and then we'll see, and you can see that how they are going. So all in one angle, right, the situation may be flipped also. So all, let us say, are non-imposters are allowed, right? Other way, all imposters are denied. So this is your receiver operating characteristic curve. So here you can see that FRR, false reject rate, and here you can see false accept, right? And now this is so if you are, let us say, this side, so what is happening? So you are, this false reject rate is increasing here, right? So what happens if the FRR is low, right? If your threshold is low, then what is there? Your FRR is going to be high. See here how it being. And what is happening if your threshold is high, then your FAR is high, and then your FRR is going down. So that behavior is being plotted here, and this is the line that is equal error rate. ER stands for equal error rate. So at this point of time, at this all these points, they are having same rates, right? Same FAR and same. So if you are here, if these error rates are small, right, then this is a perfect classification. Perfect is what? Both false accept as well as false reject, both are zero. That's the perfect, right? As you are moving towards this direction, right, you can see here FAR and FRR both are increasing. So we are moving towards poor. Now there is another version of the same thing that I will come on. Right. So here you can see that because your matcher is operating on different thresholds. So you are choosing the threshold and putting the value of, that is how it is being taught. So let us say you have chosen one value of threshold T1, right? At this T1, this is your FRR, this is your FR, right? Now let us say this is your threshold, this is your FRR, and this is your FR. And that is how this curve is being taught, right? By choosing different thresholds. Now, so so tuning of the matcher performance is actually considered as training of the arms. Here you can see that another version here. So this is the same similar thing, false positive. Right? Yes, he is given accepted, but that is wrong. He is true positive, right? So there is a here it was false accept and false reject, but here it is false accept, false positive, and true positive. Right, the same. So this is another the ROC, another version of the ROC. And here what we want the area. This is my ROC, right? And what we want area under the curve should be maximized. Means that we want our matcher to be as close as possible, right? So that my true positive rate is high and my false positive rate is low. So we want to move towards this direction, right? So here. So as close my this curve is towards this end, the better is my, right? So this is so here we say that area under the curve. So we want to maximize area under the curve. Is it clear up to this point? Now here you can see that this is the anatomy of the ROC. Here you can see these are the three different versions. And how this ROC is plotted, right? This is the situation. Right now you can see this one. What we wanted the best thing will be closer to this side, right? So here you can see the separation is more because the curve is towards this. Now here you can see that you are moving on the opposite end. When you are moving on the opposite end, the overlapping area under curve. So anatomy you can understand. Both that is the different version of ours. So you can see that when the corresponding to this curve, you can see that this is it. Now you can see it is further moving here, and they are all right? So here you can see that, and then I showed you their equal error rate. So equal error rate is a point where your FAR and FRR both are same, right? So we want, in general, if you have to choose just one parameter, we want ER to be as small as possible. because at the ER, same FARN. So when I say that my ER is 0.05, it means that both FAR and FRR, they are 0.0. So now how to compare two matches? Let us say there is a matcher A, there is a matcher B. So matcher A and matcher B. Now tell me which one is good, which one is bad? Based on our discussion, two distributions are plotted. A is better or B is better? Me दिख रहा है. Pay some attention. They are not same. Only their shape is same. They are not same. See what is happening? Remember how the probability scores were there? First your non-match and then your match. And this is completely flipped situation. Right? Your match scores small. Right? Non-match. Okay. So here you can see that AUC, area under the curve for matcher A, is 1. Right? Because there is a perfect separation. This is what we want in the perfect situation. So area under the curve is 1. But if you talk about matcher B, the area under the curve is 0 because they have flipped it. So none of the, every imposter will be allowed and every this thing then will be. Now let us say if I'm getting these sort of ROC, let us say this is for 1, 2 and 3. Which is better, A, B or C? C is the best, right? So now how there are some confusion metrics which how these rates are being calculated, this false accept rate, false positive rate and all. We will upload all these slides so nobody will get all. So here you can see true positive means all positives, all are considered as positive. Right? True negative, all imposters are considered as imposters. Now false positive, imposters are considered genuine. False negative, right? Good. So if you want to get true positive rate, out of true positive and false negative, how many true positives? These are very famous things, right? So true positive rate, false positive rate, and accuracy. So these many, if you've seen the different research papers, etc., then these many parameters. So how do we get it? Let us take this example. So these are the predicted match, these are the predicted non-match, and here it is true match and true. So true 18, false negative 2, false positive 4, and true negative 76. So what does it mean? True matches. Out of 20, 18 are true and 2 are false. So true positive rate is, similarly, out of 80, 4 are false positive and 76 are true negative. So what is the error? Error is in these 4. Right? So that is how, even if you don't remember the formulas, you can still get. So this is there. Right? And then both based on these two, you can calculate finally your accuracies. Now there are some other types of errors. For example, here failure to acquire, or you are not able to enroll yourself, right? Or you are failure to because you are not able to enroll, so you are not able to use it. If you failure to use, if you are not, if you have deployed some system and you are not using it, so that is a complete case. So here you can see FTA rate, the percentage of target population that doesn't have that power, right? That doesn't possess that quality. So how can they use it? Right? That is why you must use it. So similarly, what is the rate? Enrolled, but due to any reason, someone is not. So now, because time is less, I quickly cover up some case of identification. Right? Here, the individual is not making any claim. Right? No one is coming in saying, I am Sigma, I am so and so. Right? So, for example, you are comparing customers on the airport you are looking for a terrorist, and so everyone is concerned. So, or you can say that searching, someone is missing, and you are searching people later. So here there are two questions. First of all, is the row we are looking for that is in the database, and if it is yes, it is in the database, then who is it? Right. So these are the two things. And here there might be more possible situations, and this whole depends upon your matches, right? And how do you perform the match? Let us see some examples here. So these are the face images taken from parent database. So this is, let us say, your runtime, and these are images stored in the now. So the score. So these are the images in the database. Scores are generated, and this is your threshold. So if you look at the threshold, you know that there are two individuals which are above the threshold. So we say that, see here, there are two questions: whether probe subject is in the database, and then who is the probe subject. So we are saying that two individuals are above the threshold. So we'll say that, okay, yes, the detection is there. Some are there which are passing the threshold. And you can see the first one is the correct, right? So we say that it is a correct identification. So it is both correct detection as well as correct identification. Detection means that if for some images it is above the shoe, so you have detected. But here you have identified also, because the yes, that is the correct. I mean, highest similarity for distance, highest distance. Now again, you can see that these are your scores, and this is your threshold. Now what is happening? No one is crossing this threshold, so no detection, but actually the person is present, right? So what is there? No correct detection, and because there is no correct detection, no identification. Right? Now take the third situation. Okay? Now take. Now this time again the threshold is 0.75, and you can see that two people are above threshold, like the first case. There were also two people were above threshold. Here also two people were above threshold. So, but what is happening here? So detection is correct, right? First two are above threshold, but the first one, so you will see the highest score one, and the highest score one is non-match, right? So you say that no. So what we summarize? No correct detection, right? Because the highest score, all I mean, the desired person is present in. Now, so what is happening? If you can run many trials, right, with probe belonging to, we say this is a probe belonging to the subject in the database, and then we will see how many times your system is going to return the correct result. Right? So, so we call it, if you are saying that individual is there and you are identifying it at the first place, we are saying that, okay, it is a correct detection and identification. Now, so here you can see the threshold is 0.85. Now what is happening? Yeah. So, okay, yeah, threshold is 0.85. And all these scores are less. So, no detection is there. But the person is not. So, here you can see that it is a correct. No detect, but that no detect is correct, right? The person is not in. This earlier situation was the person was in the, right? So, here there is a correct thing. Now, here you can see again, threshold is 0.75. So, one person is above threshold. So, you will get an alarm. Yes, we have identified someone. But that is not the case, right? So, here you can see that this is a false alarm. Right? You are feeling okay, it is crossing threshold, but he is not the desired. Now, so if you run many trials with a probe belonging to subjects which are not in the database, then you will come to know about false alarm. Means the people are not there, and how many times you are getting the score more than 0. So that is how many times you are getting false. So get that rate, that is for you. Because here the how we are getting the performance, that is one case of it. So here you can see what this rank PJ, the position in the list. Their first template for the correct identity is. Yes, remember the case when there is a okay are there who are having value more than threshold. But if we are getting it at the first place, right, that is in another situation, it was there, but not at the first place. So it was not a correct identification. We are putting up the first. We are saying that, so now we need to find out at which position. If there is a positive thing, right, alarm is there, yes, there might be someone, but he is present at which position, right? So the position is the list where first template of the correct identity is written. Then we have DIR at rank A. DIR, detection and identification rate at rank A is the probability of correct identification, not at rank 1, but at rank. So what is the probability of correct identification at rank 1? Let us say 10 people are positive, right? Means 10 people similarity score is above threshold. But where we are getting the desired one? First place, second place, third place, like on which place? So we are saying, okay, how we are going to do the detection and identification at rank 8th position. Right. So what is happening here? So the rate between the number of individuals which are correctly recognized at rank A and the number of probes which are belonging to individual. So that is how you can see that based on how many are individuals are belonging to a database. Out of that, how many are going to get correctly at rank K. So that is how you right. So when you say that this DIR at rank 1, so the first one is the desired. Let us say your template is satisfied for above threshold, but it is coming at fourth position. So it is not fine this DIR 1. It is DIR 4. So at what rank you are going to get it correct? So here we say false acceptance rate or false positive identification rate, or you can say false alarm rate. Because false alarm rate are difficult, right? Your system is saying, okay, someone you're saying, okay, he is in the, because usually what is the earlier, what was the tag with the biometric? Why people don't fear to give biometric because they feel it is related to crime and all these things. So we are saying, okay, so here you can say we are saying false alarm rate, that is what we are calling as a watch list. So the rate between the number of imposters who are recognized by error, right? They are not, but still system is saying yes, they are there. And out of the total number, right? So the ratio between the two, that is the rate. So here again, what is the equal error rate? The point where FAR is different, right? That is the same. The definition of ER is not going to be changed, whether it is verification or right. So here again you can see the top one, right? It's rank 1. The correct match is top similarities. Top match. Here you will say that probability of identification at rank. Like we're talking about rank A. Have a look over there and ask question. Although it is written. But so now finally we have reached the convenience and versus security. So measure here is what convenience is always you can say reverse of false, right? So if false rate is high, obviously the convenience will be low, right? So that is there. And your false accept rate, your security is 1 minus false accept. The false accept rate is high, like imposters are being accepted, so security is low. So from that you are going to get idea, and accordingly you are going to set threshold so that you can get desired FAR. Now this is again so there are two matchers. They are represented by different color, matcher A and matcher B. Right. So if I ask you that which is more secure out of matcher A and matcher B, and which is more convenient out of matcher A and so, so in your opinion, matcher B is more secure? Here false accept rate. No, here false accept is increasing. So this is zero. Now we want to be here. We want to be concentrated at here if the security is right. So here what is happening? If you go for matcher A and matcher B, what is happening? Here you can see for this one, matcher A, your false. See, if you talk about these two, right? So false reject rate is same, but where you are getting this false accept rate. Right? Now similarly here you can see what is happening, which is having low this thing. So if you go for security, red one is better, right? If you go for convenience, blue ones. Yeah. So you can go through this. Now there are sometimes you have negative systems also, right? Negative authentication. Till now, generally we talk about positive authentication, but negative authentication. So here we will talk about false non-match, right? Reject false positive. So cost is your false positive recognition, right? If you have, because you are looking for negative and someone who is not there and you are saying, okay, yes, you are positive. So that is the cost. So this is just a summary of all the positive authentication, negative authentication, false accept, false negative, false reject, false positive. So everything is summarized here. And you can see that if you are moving at this corner, convenience is more. Moving at this corner, the security is more. So you can see that causes for false accept and false positive, they are the same, because that is how your false match is occurring, but the consequence of false match are quite. So false negative and false reject. So you can see here the difference between positive and negative. यहाँ पे the if your false accept is there, then negative there is because negative is so just reverse things. Yeah? So this is just to summarize. So says question here exceeded 3 minutes.